Hello everyone, welcome to the newest installment of Pre-Calculus Lessons from Home. Today we're going to cover section 5.7. This is ArcTrig, and I will explain what that means in just a moment. Is this readable? How's that? Better. Okay. So, start with a quick review. In section 5.4, we looked at a lot of problems that looked like sine of 30 degrees equals something, cosine of, let's say, 4 pi over 3 looked like something. The tangent of 7 pi over 6 looked like something. And for the most part, we would find these angles on our unit circle. We would look at the y value of the unit circle for sine, the x value on the unit circle for cosine, the ratio y over x for tangent, once we found these angles. And we found that the sine of 30 degrees is 1/2. The cosine of 4 pi over 3 is, let's see, that's third quadrant, close to the y-axis, so that's going to be negative 1/2. 7 pi over 6 is also third quadrant, but close to the x-axis. So your y value here is going to be negative 1/2, and your x value is going to be negative root 3 over 2. So after you simplify this, you probably get root 3 over 3. And this is the benefit of the unit circle. Unit circle lets us take angles as inputs. We can take angles as our inputs for these trig functions, and we can use the unit circle to find our y values, our x values, ratio of y over x on the unit circle, to find these sine, cosine, tangent values very easily. So, section 5.7 is about flipping this. We're going to look at something called the arcsine, and eventually the arccosine and the arctangent, but we're going to start with arcsine as sort of a understand what this means and how it behaves topic. And the arcsine, we will soon discover, is the function inverse of the sine. So sine of theta equals some number. This is an angle as our input. And this is a y value on the unit circle as our output. That's how the sine function behaves. We talked a while ago about how functions are, you can think of them in terms of input and output. Every input has exactly one output. Here your inputs are angles and your outputs are y values. So the function inverse flips the input and the output. So if we're talking about the function inverse of sine, I'm going to write that as arcsine of some number. The arcsine of some number is going to be an angle. So if I ask you for the arcsine of root 2 over 2, this is a y value on the unit circle. We've flipped this input-output situation. So now the input of this function is a y value on the unit circle. And the output of this needs to be an angle. So the arcsine of this particular y value on the unit circle should probably be pi over 4 radians or 45 degrees. Is that readable? There we go. So this is our first pass. Relatively straightforward. Flipping inputs and outputs on the sine function. We can do the same thing with cosines and tangents. The arc cosine of, let's say, 1/2. Typically, a cosine would take an angle as an input and produce an x value on the unit circle as an output. So if we're doing an arc cosine, those things are flipped. And this is an x value on the unit circle. And the output should be the angle associated with this x value. So this one is probably pi over 3 or 60 degrees. And we can do this with arctangents as well. If I ask for the arctangent of -1, this is going to be a tangent. Usually takes an angle as an input and gives you a ratio of y to x values as an output. So the arctan is going to take in a ratio of y to x values and give you an angle as an output. If the ratio is -1, that means that the two numbers, the x and y value, have the same magnitude, but opposite signs, which means that we're probably at either 135 degrees in the second quadrant, which is 3 pi over 4. So these are just some basic, familiarize ourselves with the arc cosine, arctangent business. Here's where things regarding arcsine, arc cosine, arctangent, here's where things are going to get a little weird. These angles that I have written here, pi over 4 for the arcsine of root 2 over 2, 45 degrees for the arcsine of root 2 over 2. These angles are not the only angles that give me a sine value of root 2 over 2. This is not the only angle that gives me a cosine value of 1/2. This is not the only angle that gives me a tangent value of -1. So let me talk about that a little bit. I'm going to start with the, I'm going to work with this arc cosine at first, mostly just because it's on top. If I want an x value of 1/2, that means that I either need to be up here or down here. This is your, if you're looking at a coordinate grid, this is x equals 1/2. X equals 1 would be right there. There are two angles on the unit circle that will give you an x value of 1/2. Pi over 3 is the top one. 5 pi over 3 is the bottom one. So this has two angles that give me the same cosine value. And that's kind of a problem. But wait, there's more. We remember from section 5.1 that we talked a lot about angles being coterminal. This angle, pi over 3, that is coterminal with 7 pi over 3. You can just do a full rotation and come back to there. This thing is coterminal with 11 pi over 3. I shouldn't use equals, I should say coterminal. It's also coterminal with negative pi over 3. You could just go down here and get that. Also coterminal with negative 7 pi over 3. This one is also coterminal with 13 pi over 3, negative 5 pi over 3. I'm going to say dot, 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 because I could keep doing this for hours, but I don't want to. The moral of this story is, for any given x value on the unit circle, there are infinitely many different angles that will produce that x value as its cosine. The cosine of every single one of these angles is 1/2. Which makes sense if you think about what cosines look like. We just spent a lot of time in section 5.5 graphing cosine functions. If we're just looking at y equals cosine x, that graph does this. And also this. This graph will keep on bouncing back and forth forever in both directions. It's going to hit 1/2 as its cosine value. It's going to hit that here, and 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 infinitely many other places. The number of angles that have a cosine value of 1/2 is infinite, which is a problem for us. At the very beginning of the semester, I asked all of you what function meant, and we decided that a function was an equation with two variables. X was the input and y was the output, and each input had exactly one output. This is what we said a function was, and for those of you who have stumbled upon this YouTube video watching from home, who might have taken some advanced math courses, I know that this is not the actual definition of function. This is a working definition of function for Precalc. It'll get the job done. This definition of function that we are working with for now says that each input has to have exactly one output in order for this thing to be a function. And we do want this thing to be a function. If this is a function, then we can do fun things with it. We can graph it, when we get to calculus, we can take derivatives of it. There's lots of benefit to this being a function. So we want it to be a function. But right now it's not, because each input, an input like 1/2, has infinitely many outputs. If I'm just looking at an angle that produces this cosine value, there's infinitely many of them. I don't want that to happen. So what I need to do is I need to create a range restriction on this thing. We've heard of domain restrictions before, and we're going to need to do that as well. But the more pressing concern right now is that we need a range restriction. Domain restrictions happened when we were playing with functions that there were certain numbers that we were not allowed to plug into the function. Things like f of x equals 1 over x minus 3. If this is your function, you can't plug 3 into this function and get an output. So this has a domain restriction. Range restrictions are going to work kind of the same, except instead of restricting what we are allowed to plug into the function, they're going to restrict what we are allowed to get out of the function as an output. This is going to be a range of values, a limited range of values that this thing is going to produce as answers, so that I'm not getting multiple different outputs for the same cosine x value. And for that, I need to think about what this range should be. I want a range that covers all possible outputs exactly once. So we think about cosine being x values on the circle. I need a range of angles that will cover every possible x value. X equals 1 is the biggest I can get, x equals negative 1 is the smallest I can get. I need something that will cover every possible x value exactly once. And I need this to be a range of angles. And honestly, the easiest way to do that is to go from here to here. This is theta equals 0 as our starting point, theta equals pi as our ending point. This range of angles will cover all of these possible x values exactly once. If I kept going around the circle down here and finished the circle, it would cover these x values twice. Once on top, once on bottom. I don't want that. If I only went to 90, it wouldn't cover the back end. I wouldn't be able to get negative x values. So I need to go all the way from 0 to 180. Or maybe I should say use these degrees. 0 degrees, 180 degrees. So I'm going to go from 0 degrees to 180 degrees. That's going to be the range restriction we'll place on arc cosine so that it can be a function, and each input as an x value on the unit circle will have exactly one output as an angle in this range. So now instead of the arc cosine of 1/2 being pi over 3 or 5 pi over 3 or negative pi over 3 or 7 pi over 3, it's just going to be the one angle of all of those that is in this range, which is right here, and that's pi over 3 as the only answer. That's arc cosines. Next, we need to talk about arc sines, because they have the same problem. But we're going to solve it in a very slightly different way. The example I used before was arc sine of root 2 over 2, but I'm going to use, we'll still use that one, arc sine of root 2 over 2. This is a good one to go with. So we said earlier that the arc sine of root 2 over 2 should be pi over 4. But if we think about root 2 over 2 as a y value on the unit circle, that happens about here. That'll happen here at pi over 4. And it will also happen here at 3 pi over 4. And again, it will happen at anything coterminal to these. If you go around this way, it'll happen at negative 5 pi over 4. It's going around like this. It'll be coterminal with this 3 pi over 4. If you want to go all the way around, you could say negative 7 pi over 4 is coterminal with this, going backwards. You could start doing laps. You could say it's 9 pi over 4, coterminal with 9 pi over 4. So again, there are lots and lots and lots of different angles that will have a sine value of root 2 over 2, which is not what we want to have happen in a function. If arcsine is going to be a function, it needs to have exactly one output for each input, which means that, once again, I need to restrict the range of the arcsine so that it's producing exactly one answer every time I plug in a number.